Okay, so today we're going to tackle 19.6 and we're going to do a little bit more application of what you did in the last video. Now the focus on the last video really was, let me go back here, this equation here, where we looked at how the Gibbs free energy, whose sign tells me whether the reaction is thermodynamically favorable or not, and it's a combination of delta H and delta S with temperature. So if I were to kind of summarize for you, if delta H is negative, that's thermodynamically favored. When delta S is positive, thermodynamically favored, and delta G is negative. So when I'm looking at all of them, we looked at here, if my system has all of these three things, I know it's thermodynamically favored. But what if this one's favored and this one's not, or vice versa? How are we going to do that? Because that is the, not the extremes. So if this is negative, which means this is exothermic, and remember exothermic reactions are favored, and this is positive, the sign of delta H is always negative. So that means it meets all these conditions. It's always, I don't even have to calculate it. On the other hand, if this is positive, which means this is endo, which is not thermodynamically favored, endo means I have to put energy in it. And this is negative for a certain process, which means I'm tending towards disorder, then delta G must be positive. So these are the two extremes. Where both delta H and delta S are thermodynamically favored, and here, well, delta H and delta S are not. So we know that in that direction it is not favored, but in the reverse it would be. All right, so now let's look at something in between. So I'm going to put the equation up here again. If delta H is negative, right, which means it's favored, and this is negative, which means it's not, this would be thermodynamically favored at low temperatures and not favored at high. Why is that? Well, if this is negative, then I don't want this to be too high, because then, although this is favored, this will overpower this one and make this positive. So this is only favored when T is low. However, when delta H is positive and delta S is positive for a certain process, which means that this is not favored and this one will be favored at high temperatures. Why is this? Well, if this is positive, I want this whole thing to be negative, so it's minus a really big number, and that's a high T. The way you can work through these problems, if you get them on a multiple choice, is just put some numbers in there. Use ones and twos and whole numbers, and you can probably work it out. Now, the Gibbs free energy, let's use this equation to do a calculation. Here's my reaction. Here are my two values. The delta G for this one is going to be, bracket, negative 196.6 minus, oh, sorry, I don't need to do brackets here, do I? 750 K. Remember that your temperature must be in K. You need to watch for that. And again, now that we're combining terms in one equation, this is in kilojoules, so I'm going to actually put that. I've got to convert this to kilojoules, so I'm going to divide by 1,000, and that gives me negative 0.1896. And that's negative 1896 kilojoules, and that equals a negative 54.4 kilojoules. Now, let's look at a slightly higher temperature. Well, not just slightly, a very much higher temperature, because this is energetically favored and this is not. So when I'm at this temperature, I get a negative, but let's raise the temperature. Remember, we said that if this is negative and S is negative, which I have here, this is going to be favored at low temperature. So that's that temperature, it's favored. Let's see what happens if I raise the temperature. I get negative 196.6 kilojoules minus 1250 times a negative, negative 0.1896, and I actually get a positive 40.4 kilojoules. Once I get up into these higher temperatures, just like it says here, it becomes not favored. Okay, so let's look at some other scenarios here and actually start applying delta G conceptually, and then we're going to introduce another equation. So I've got delta G is 0 when a system is at equilibrium. Calculate the temperature at which the reaction in part E, so that would be here, would achieve equilibrium. Okay, so what we're going to do is delta G is equal to 0. And this is a very common problem. They're going to expect you to know that if I give you H and S and I'm at equilibrium, this is 0. Therefore, 0 is equal to delta H minus T delta S, or delta H is equal to T delta S, or T is equal to delta H over delta S, which is negative 196.9 kilojoules. So I'm over here, up here. Again, I'm gonna convert that into joules. This is negative 1896 kilojoules is equal to 1037. Okay. So at equilibrium, this is 0. So what do I need to do? The question would be, what do I need to make this favorable? Basically, to make this favorable, if we go below 1037, then the reaction will be favored. All right. Now, what we're going to do is we're going to calculate everything, and we're going to do the same process. We're going to be given delta H, formation, delta S. We're going to calculate those. Then we're going to establish equilibrium, and then we're going to look at how the values compare. Okay, so this would be a typical kind of, this is more of an FRQ problem where they want to make sure you know how to calculate delta H, delta S. So let's do that. Delta H for this process here, remember I can look these up, I've got these all right here, is going to be products minus reactants, which is 0, because now remember how states matter. These are both elements, but the elemental form or state of bromine is a liquid. You'll see this with iodine also. The elemental form is a solid. So make sure you're very careful, especially with the diatomics, what state you're looking at, because this would not be 0, but this one is 0. And that is going to be plus 30.71 kilojoules. And then delta S is 0. Now remember, I've got to convert both of these to kilojoules because they're in joules. We've got to remember to do that. 53 minus 0.1523 is equal to 0.093 kilojoules. Okay, so delta G is equal to 0. So that means delta H minus T delta S is equal to 0. Delta H is equal to T delta S, because what we want is when a pure substance is at its normal boiling point, that's equilibrium. What is the normal boiling point? Remember that when we are going through a phase change, when we are converting the liquid to the gas, we're at that plateau, right? So I got like this. This is the melting point. And this is the boiling point. So I want to know what that boiling point, and that this is equilibrium. That there. So that means that when G is equal to 0, I'm on the plateau. And in this case, I'm on the top plateau because I'm going from a liquid to a gas. So I'm right here. All right? So T is going to be delta H over delta S, which is 30.71 kilojoules divided by 0.093 kilojoules, which is equal to 330 K. If you look up the boiling point for the equilibrium, where the normal boiling point for bromine is, it is, I think it's actually 332.4 or something K. So we calculated that using the concept that when we're on that plateau in a phase change, the plateau delta G is equal to 0. And so I can calculate the temperatures at the plateau of that cooling curve. Okay. Now, predict if the evaporation of a bromine should be thermodynamically favored at 200 degrees K. Now, we have calculated the normal boiling point here. Assume that the values of delta H and delta S do not change with temperature. Now, 200 K is below 300 K. So what I'm going to do is I'm going to calculate it. I'm going to use the delta H and delta S that we calculated here, the actual values, and let's just plug it in. If I'm being asked, is the reaction thermodynamically favored? That is a delta G problem. Right? If I want to know if it's thermodynamically favored, that's a delta G problem. So let's plug it all in, which is 30.71 kilojoules minus, we're going to put 200 K in here, 0.93 kilojoules is equal to a positive 12.1 kilojoules. So a positive 12.1 means that this reaction is not favored.